So before going on, I will try to make a little introduction on what is AvanAD. AvanAD is quite a new name right now in the Alliance. It's new because it acquired DNAe2c. So it has been founded in 2020. In 2023, it acquired Trainendable, which was a company specialized in ECC. Then we get around a founding last year by United Venture. And this April of this year, we acquired DNAe2c. The goal of AvanAD is being the first cyber storage company in Europe. So the reason why, what is the cyber storage, we will see in the next slide. But the first, let me say, goal of AvanAD is follow what the market is right now, that is data repatriation. So right now we see that a lot of company, 85% of the company will like to have the data on-premise. So on-premise or on the edge, like they say, and not use the cloud anymore. There are a lot of reasons. The first reason is the first model that has been designed by Gartner. So the reason is cost, because cloud is not so cheap as they promised at the beginning. Compliance, complexity, and lack of control. Because a lot of companies, especially enterprise companies that have sensitive data, they understand that they do not know exactly where the data are stored. So that's the main reason they want to take the data back. Then, and today it's a very critical discussion, it's the geopolitics environment that we are living today. In addition to that, we have the safe AI. So we already spoke about AI also in error correction, but using AI with sensitive data on cloud is not something that the company want to do anymore, because data are not encrypted, because data, we see hard data breach every day, so they want to use AI on their data on-premise. So that's the reason why AvanAD has been founded. So what is cyber storage by AvanAD? So it's made by three main ingredients. The first one is advanced cyber shields. Of course, we're talking about cybersecurity, but it's not a new level of cybersecurity made on the hardware level. So AvanAD has also its own SSD that is manufactured in Italy. So a lot of, let me say, cyber control are made at the hardware level. Then your own data governance, because we have an operating system and we know exactly where the data are stored. So we can provide our clients and describe exactly where the data are stored. That is something that is demanding right now. And of course, tailored secure hardware. Since the hardware is made by AvanAD, of course, we can also custom it, we can tailor for our clients, and it's secure in the sense that it's made by our own. But then, why DNA? We are a storage company, so why DNA? The reason is that right now, today, cyber storage, let me say the standard storage, so flash storage mainly, but also hard drive, is quite secure enough. But what about the future? The future can be DNA storage, and DNA storage will have new challenge also in terms of security, because it will introduce a new concept of security. There will be the standard, let me say, cybersecurity here that we already discussed about, so cyber shield and so on, but another level, or biosecurity. We will have a lot of session tomorrow about biosecurity, but of course it's a new challenge that synthetic DNA will pose. And that's the reason why AvanAD decided to acquire DNA, also to understand the challenge of security in the future of the storage. Okay, So I will go fast with this one because, of course, everybody here know already the benefit of DNA. But just going fast. So what introduced DNA, why it is the future, it's so promising, it's because it has extreme storage density, long-term durability, sustainability, and low environmental impact. And we know that now the power consumed by data center is really huge. So the future of the storage, if it is DNA, it will decrease this a lot because it's not required some fan coil and so on. Long-term stability, and then it's what the nature decided to store data. So nature decided to store data on DNA. So why can we follow nature? And then DNA is the basic of the life, so we will always be interested in reading DNA, because it's our foundation. So it's not something that we need to fight against the obsolescence. That is something that all the storage has. What are the challenges? The challenges right now is high cost, slow read and write speed in comparison with standard storage, error rates. So this is the main topic here. The DNA channel is much more different than standard storage, the standard channel. There are errors that are much different in the sense that in the standard storage there is just substitution. Here we have insertion, deletion, and also erasure, because the strand can be lost. So we need to adapt something that we know from the codec area in a channel that is much different. Then we have limited accessibility and infrastructure, because of course, and here it is an example, we have to come together, biotech company, storage company, company that develops algorithm and IP. So there is a lot of knowledge together to make it work. So it's not easy, it's not for everyone. And then ethical and regulatory concern. Of course, also this pipeline, we already saw that, but this is just to say that, of course, we are not a biotech company, so that's where we work, so data encoding and, of course, decoding. And there are 3 pillars in what we say, in what we do. So the first one is building noise model. And why it matters, we already saw in the previous presentation from the Technion guys, because experiment will take a long of time and are very expensive. So we need to build model in order to understand how to apply codec on that. Then we want to develop encoding and decoding IP, and for that we use a simulator, also in Avanade. And this simulator is called DNAe2c, and it's used to test and to benchmark of the codec already in the state of the art. We use also experimental data to see how different algorithms and different codec will work. So why a simulator? We already saw that, but I would like to remind that. Because if we want to look at encoder and decoder side, let me say, it's an algorithm, they're just equation. But how that equation works, it depends, sorry. Okay. It depends on the noise. But the noise, for definition, it's randomic. It's statistical. It has a statistical behavior. So how can we understand how an algorithm works on something that is randomic, that is not deterministic? That's the reason why we built a simulator. Because in this case, we can really simulate tons of data, and also with facility like Tristan described this morning, we can really simulate tons of data and apply different algorithms and see how they behave. But why we focus on ECC? Also, the Alliance focus on codec. Why? There are a lot of challenges in the synthetic DNA. But ECC is not just an algorithm, because we already had some examples where ECC was able to enable a technology. This is just an example. So in the late 80s, everybody has the phone at home. But at some point, internet break up. But there was already an infrastructure based by phone wires. How can we use a medium that was not made for tons of digital data to transmit tons of digital data through internet? It was through the use of ECC. So in this case, the ECC was able to enable high-speed communication over a medium that was not created for that purpose. For the guys that work on the storage, this is another example, the NAND flash. NAND flash was a really emerged technology because it was fast, it's scalable, and cheap, and so on. But it has, by definition, a lot of errors just when they got manufactured. And the reason is that the errors occur in this region where two distributions overlapped. Right now, this is the technology as of today. Here, where you say just two distributions, there are 11, 32 distributions. So, of course, just when it go out from the industry, the NAND or the distribution of the data stored in the NAND already overlapped. So, how can we use a medium that has a probability of errors of 1 bit over 100 to store data to a probability that has to go there in order to compare to a hard drive? It was through the use of ECC. NAND flash and solid-state drive right now that are based on NVMe, for example, use very strong error correction code in order to recover data. Otherwise, the medium is not reliable at all. So also here we have a very promising medium because it's stable, it has a strong retention, a high capacity and so on, but there are really a lot of errors. And the process to synthesize and to sequencing are one reason of why they are so long and so expensive is because they have to be quite precise in their reading and their synthesis. Otherwise, the number of errors will really explode. So also here, maybe if we have a system that is more tolerant to error, maybe we can allow less precise synthesis and sequencing. Maybe also in this case, the ECC can play a role to enable a new storage, so a new technology. Okay, this is just the basic of the ECC. So ECC, they were discovered, let me say, for telecommunication. And basically, standard ECC are block codes. So why it's not possible to use, for example, block code, the standard block code, without anything adding on it for DNA? It's not possible for, sorry again, for the number of errors. Because suppose that at some point, this is the source data are encoded and mapped. At some point, to the channel, we have an IDS channel, so we have insertion, deletion, and substitution. This is the message that we get back. We get one substitution and one insertion. We got the reverse mapping. This is just a talk example. But at some point, here, you just use Hamming, so it's really a toy example. We need to compute syndrome. So just to perform a multiplication of this message, this digital message, by a matrix. It's not possible, because the length is not the same. Because, of course, Hamming has been built just for substitution. Here we got insertion, the length is not the same, so it's not possible to use it. As it is, we need to make something. So, when we use block codes and IDS channel, and that's the reason why it's so complicated to have all the decoding pipeline together. It's not enough to just have an error correction, a powerful error correction, because all the algorithms work in synergy together. If the length, for example, is not correct, and we can detect that, we may decide if we want to discard it, if we want to read something else. We must make decision. And this decision, of course, will have an impact on the error correction side. In addition to that, this is very important. In addition to that, of course, this is not a standard channel, so it does not rely on just Hamming distance, but on Levish time distance, so, which is much, much more complicated, not only on the computational side, but also from a theoretical point of view, because it doesn't have the nice property of the Hamming distance. So what we decided to do? We came up with this new code that we call DNAe2c. The acronym stands for DNA Noise Aware Error and Erasure Cleaner. When we tried to develop a new code, what we had in mind was this bullet. So basically, we say that it's not possible, it's not easy to have a single ECC for all the technology. Because, for example, sequencing technology can vary really a lot. So the ECC must be different, but we do not want to have too much different ECC. We just want to have the same, let me say, infrastructure on the ECC point of view, and change parameters or adding something on it, so that it can be used with all the technology. Then, of course, we need a lot of simulation. We use partially real data and, of course, randomic data in order to perform that. Then we want to maintain the high code rate. We already discussed about the code rate. So we do not want to introduce too much data to synthesize. So we do want to keep the capacity of the DNA high from the point of view of the user data. But we want to be able to change it, because code rate is very powerful. For example, if the number of errors increases too much, we can decrease that. So we must find out a code where it's easy to tune the code rate. And then, since we want an ECC to be ready for end-to-end platform, we want to implement it in hardware. That was very challenging, because sometimes it's quite, let me say, easy to find out nice algorithm with nice equation and see that they perform well, but they're not feasible in hardware. So we not just want to make R&D project. We want to have a solution that is ready for end-to-end platform. Now the solution is a proprietary code that is iterative. And the reason why it's iterative, because in this way we can change the latency. So we can also measure the time that we spend to decode that. Then it has a flexible code rate, as I mentioned, so that we can change the number of parity bits. And we have this, I just call it tricks. So it's something that we can add, enable or disable on the code side, so that if we see that the channel condition are, for example, an increased number of erasure, we can add something so that we can still decode it. And then it's hardware implementable. So how it works right now, we create a noise model. Then we let me say, trying to find out the best parameters of our code in order to understand if we are able to decode that. And then we input the model in our simulator. If we are happy with that, we're done. If we're not happy with that, we have a lot of parameters and decoder and so on, we change something. We perform, again, another round of simulation and so on. That's the reason why we need also hardware co-simulation, because you can see that this loop can be really, really high. So Christian already showed this graph this morning, but I will show you it from the ECC perspective. So right now we have, in standard error correction, let me say books, we have bit error rate versus frame error rate. Here we do not have bit, because it's not just bit error rate, it's not substitution anymore alone. So we need to split the graph and understand how the frame error rate behave in comparison with a lot of quantities. Here it's just an example. Here we have a number of deletion and insertion. We fix the number of substitution here, we move the number of deletion and insertion, and we see how the code behave. So, and of course, it's a simulation, so there are a lot of data. This is all the simulation set that we used in this kind. So what we see here, sorry again, is that, for example, if we fix a frame error rate of 10 to the negative 9, that means that we accept to lose a frame over a billion. Our code is able to recover from this value of deletion, this is from RS, so Reed-Solomon codes, to this number. So we have this incredible gain in the same condition in comparison with Reed-Solomon. So we can support a number of deletion, which is an insertion that is 10 times more. Another parameter, of course, is the probability of losing a strand. So what happens if we lose a strand? In this case, if we fix the drop rate, for example, this number, we see that this is the graph of Reed-Solomon, this is our graph, and we have the dropout rate in comparison to the frame error rate. We see that we gain 2 orders of magnitude in comparison to Reed-Solomon. So I will go fast with that. It just what I said before. Every time that we design a code, we have our standard code with our parameters here, and studying the channel, so the real data, we can tune the parameter and adding these tricks, which can be very different depending on the error condition. Here is something that we already saw this morning. Of course, is the code is implemented on FPGA. And we go with conclusion. So a new storage right now is essential because it's not feasible to just use data center anymore. DNA's data storage is a strong candidate, and error correction code can enable this technology. The decoding and encoding are complex. It can be studied through the use of a simulator. DNAe2c is our simulator, and we use that to explore and optimize encoding and decoding strategy. And at the end, we came up with this proprietary error correction code, DNAe2c, that is flexible and is a complete solution. It can be tuned depending on the technology, based on the real data, and it can achieve a target frame error rate. Thank you.
Questions? Yes, we have one here.
Thank you for the nice talk. My question is, do we perceive a relationship between error rates and the cost of synthesis and sequencing? If so, how much reduction in cost and time we gain while relaxing synthesis process?
Okay, in this case, it's not easy to answer this question because basically we develop algorithm. That's why we have a lot of partnership in case, in order to understand and make, let me say, it's not hardware software, it's real and software simulation in order to tune parameter and make a real experiment to see if, for example, going faster, that's an example of synthesis, they have, of course, a number of errors that is much higher, but we can still recover.
Thank you.
You're welcome.
Okay. So I think if there are more questions, maybe can ask afterwards for the time control. So
sorry.
Thank you. No, it's okay. Thank you, Alessia. Thank you very much. A round of applause.